The idea of the Great Blast has shaped our understanding of the universe and provided the foundation for modern cosmology, also referred to as coarse-reading cosmology, which is based on Einstein's conjectures. The cosmos started to develop at the same moment as the massive explosion, which signified the creation of all matter, energy, and presence. This event, which occurred roughly 13.8 billion years ago, is what led to the colossal universe that we see today. Late advances in cosmology, however, suggest that the colossal blast was probably not the beginning but rather that, from our perspective, there may have been a period preceding the massive explosion that was equally important in shaping the universe. We call this pre-period incalculable expansion. One of the most fascinating aspects of modern cosmology is probably development. It implies that the universe underwent an incredibly rapid emotional growth prior to the hot, dense period of the massive explosion. The universe was expanding at an alarming rate during this time. The cosmos would have expanded to be unfathomably larger than the entire discernible universe in a tiny fraction of a second, roughly 1/4,000,000th of a second, to illustrate just how ridiculous this extension was, presuming it started off smaller than an atom. Despite its brief duration, this extension stage played a crucial role in the universe's formation. The energy causing this extension was released into space after the inflationary period ended, warming it and creating the matter particles that comprise everything we see in the cosmos. Development is the precursor to what we think of as the Great Explosion in many respects. Even while the extension hypothesis is now widely acknowledged in cosmology, there are still many unresolved issues. For example, we do not yet know what triggered development, what halted it, or how long it lasted. It is important to take note of these unanswered cosmological questions in order to have a better understanding of the universe's origins. Prior to development, the cosmos was a peculiarity, a startlingly dense small area of substance. Development started from this oddity and ultimately resulted in the configuration of atoms, particles, stars, and worlds. The idea that the colossal blast was the beginning of everything is intriguing, but modern cosmology suggests a more nuanced scenario. According to certain theories, the cosmos went through a phase prior to the massive explosion. During this time, extension caused the universe to develop at an astonishing rate, essentially increasing in size by a factor of 1,000,000,000,000 in a split second. A strange structure of energy that pierced vacuum space propelled this rapid extension. When extension was finished, the energy that had propelled this evolution was converted into particles, warming the cosmos and causing the hot, dense condition known as the giant explosion. Despite being chilly and empty, this inflationary phase prepared the way for the creation of matter and the modern universe. The concept of timeless expansion is one of the most theoretical ideas in modern cosmology. According to this theory, expansion didn't stop all at once but rather stopped in different places, forming a variety of pockets that could potentially be a separate universe. One of these patches would represent our universe. Everlasting expansion suggests that there may be an infinite number of these universes, each with a unique set of real laws and constants. The notion that our world could be one of many, if not an infinite number, of universes is where the potential of the multiverse becomes crucial. It would explain why our cosmos is so well suited for life if this theory turns out to be true. Every possible combination of real laws might exist in multiple universes in this multiverse scenario, and we get up in one where the conditions are ideal for stars to form and for carbon, oxygen, and other elements essential to life to exist. The potential of expansion itself is supported by empirical evidence, although theories such as the multiverse and perpetual expansion are still theoretical. The universe's most seasoned light, the cosmic microwave background radiation, CMB, provides the most solid evidence for expansion. About 380,000 years after the massive explosion, when the cosmos had cooled enough for atoms to form, the CMB was sent out. The universe had become simple by that time, and this light has been moving through space ever since. Cosmologists can basically take a newborn picture of the cosmos by focusing on the CMB. Researchers can better understand what transpired shortly after the massive explosion and provide evidence for the inflationary model thanks to the light, which provides fragments of information about the early history of the cosmos. The European Space Agency's Planck satellite, which captured in-depth images of the CMB, made one of the most important discoveries. These images show subtle differences in the early universe's temperature that are consistent with inflationary theory predictions. This experimental data confirms that expansion is a key component of our understanding of the universe's origins and not just a theoretical idea. Einstein's general relativity theory and the quantum hypothesis, two of the most important theories in modern physical research, must be combined in order to determine the cause of the massive explosion and what before it. The conduct of planets, stars, and universes on the largest scales is depicted by general relativity, whilst the conduct of particles on the smallest sizes is depicted by quantum theory. Researchers should create a theory that combines these two frameworks in order to address the main questions in cosmology, such as the composition of the universe and its origin. This would allow us to understand the circumstances that led to the colossal blast as well as the explosion itself. The immensity of the universe is among its most startling features. The perceptible universe is around 94 billion light-years big, with the furthest objects we can see being about 47 billion light-years away. Considering that the universe is only 13.8 billion years old, this might seem unusual. In the age of the universe, how could the visible cosmos be larger than the time it would take for light to travel through it? The fact that the cosmos has been expanding over time provides the answer. The distance between objects increases with the size of the cosmos, making distant objects farther away than it would take for light to reach us. The majority of scientists acknowledge that the cosmos extends well beyond the observable universe. In fact, it is possible that the cosmos as a whole is infinitely large. The portion of the universe that we can see, limited by the amount of time light has had to travel after the massive explosion, is known as the detectable universe. We may never be able to see some of the universe's vast regions. Even though the cosmos might be infinite, the question still stands. Is there anything beyond the universe? The majority of researchers are a little unsure about this idea. There is no outside to the cosmos, assuming it is infinite. In essence, the cosmos would continue to exist indefinitely. Whether the world is limited, discussing anything outside of it is unlikely to make sense. The possibility of past the universe most likely won't have any physical significance because past would imply something outside of space, which is a feature of the universe itself. Just as the beginning of the universe is a topic of great interest, so too is its unavoidable conclusion. The universe will continue to expand indefinitely, which is currently the best indicator. This is anticipated because to an oddity called dull energy that is accelerating the expansion of the cosmos. Prior to the discovery of dim energy, scientists believed that the gravitational pull of the universe would eventually cause its expansion to slow down. In fact, there was a chance that the universe would stop expanding and begin to contract, which would cause a huge crunch. But it appears that dark energy is rapidly tearing the universe apart. The universe will eventually reach a situation where galaxies float so widely apart that they become segregated from one another if this acceleration keeps up. The universe would get weary, dreary, and frigid in this scenario. Worlds would drift apart, stars would deteriorate, and matter would eventually decay. This is currently known as the universe's Big Freeze or heat death. One of the most important and intricate stories in science is the story of the universe, from the massive explosion to its possible demise. The idea of expansion and the study of the huge microwave background have taught us an amazing arrangement about the origins of the cosmos, but many questions remain. Why did expansion begin and stop? Beyond the observable cosmos, what is there? How many different universes are there if there is a multiverse? We will undoubtedly learn more about these riddles as scientists continue to focus on the cosmos using advanced invention and theories that connect general relativity and quantum mechanics. The journey to understand the cosmos is ongoing, and each revelation takes us one step closer to recognizing the profound questions surrounding our existence. In addition to being a logical endeavor, the study of the universe's origins and structure poses philosophical questions about reality, presence, and our place in it. The nature of dull matter, which is thought to comprise roughly 27% of the universe's mass-energy content, is a major topic of study in cosmology. Because dull matter doesn't emit, absorb, or reflect light like normal matter does, it is both undetectable and perceptible solely through its gravitational effects on noticeable matter. Understanding dark matter is essential to understanding how universes form and behave. The features of dull matter have been partially revealed by evolving research and perspectives, but its precise nature remains elusive. Weakly interacting massive particles, WIMPs, axions, and other exotic particles are among the few applications that have been suggested. Nevertheless, no direct evidence of dim matter particles has been discovered thus far. The hunt continues through a combination of astronomical observations, terrestrial experiments, and simulations that simulate the effects of dim matter on the development of the universe at massive scales. Dim energy is another important field of study. The power behind the universe's accelerated expansion. Approximately 68% of the absolute mass energy content of the cosmos is made up of dark energy. Its unexpected discovery has led to a number of theories, such as the cosmological constant and dynamic fields like quintessence. Determining dim energy is crucial since it will determine the universe's extreme fate. Scientists are focusing on how it affects cosmic structures and trying to determine if it changes or stays the same throughout time. The study of large-scale structure creation provides enormous insights into the universe's collection of experiences, despite dull matter and dull energy. The incomprehensible designs we see today are the result of how matter bunches together under the influence of gravity, as shown by perceptions of the inestimable web, a vast organization of systems, bunches, and fibers. Supercomputer-powered reproductions help experts comprehend how these structures evolved over billions of years and continue to progress. Additionally, as scientists attempt to determine the conditions necessary for life beyond Earth, astrobiology and cosmology come together. With thousands discovered in recent years, the search for exoplanets, planets orbiting stars outside of our planetary group, has intensified. Some of these exoplanets are located in the habitable zones of their stars, which may be the ideal environment for the presence of fluid water. Researchers seek to gain a better understanding of the conditions that make a planet conducive to life and the possibility of life elsewhere in the cosmos by taking into account these distant worlds. Finally, it is impossible to overstate the role of fundamental material science in cosmology. Physicists continue to be challenged by the search for a bound unified theory that unifies quantum mechanics and general relativity. The goal of theories like loop quantum gravity and the string hypothesis is to bridge these two fields and provide explanations for anomalies like black holes and the early cosmos. As innovation advances, so does our ability to observe and interpret huge oddities. Because they provide incredible detail of distant systems and cosmic events, space observatories like the James Webb Space Telescope are changing our understanding of the universe. We go closer to solving the puzzles of the universe's structure, development, and extreme fate with every new insight. The study of the cosmos is a complex tapestry of philosophical thought and logical inquiry. From the fundamental forces that create vast structures to the search for extraterrestrial life, our research is an example of humanity's tenacity through curiosity in the cosmos as we work to find the answers to these important questions and, in the process, gain a deeper understanding of the universe's immeasurability and complexity.